we are going to learn about hash tables. And so number one, you have the hash function. And number two, you have an array of elements. And these array of elements are generally an array of nodes. And because having a node allows you to have a linked list to each of the nodes. And basically, each slot in the array acts as the head of a linked list. So essentially, this points to another element, which can also point to another element. So basically, using this, as stated earlier, you can have extremely fast lookup, insertion, and deletion times. So what is a hash function? A hash function is a function where you pass in the element that you want to place into the hash table. And basically this function, for example, if you wanted to hash the letter A, it will go through a series of complex calculations and end up returning a number. For example, let's say 1. And this number corresponds to where you're going to put the element in the array in like which index. So if we have an array of 0, 1, 2, 3, if the hash function returned the number 1, then we would place it into the 1 slot, and now we would have A in here, hypothetically. So this scenario would happen if we were ignoring the linked list attribute of a hash table for now, just to make things simpler. So just as another example, let's say we wanted to hash the letter B. So if we hashed B, maybe we'll get a return value of, let's say 2. And that means that B would end up going into the second index of our array in the hash table. Now, generally, you do not need to write your own hash functions because they can be incredibly complex, and the best hash functions in the world right now are have really complicated mathematical computations. A common hash function that you can use is called djb2, which can be very helpful in the Speller p-set. So what's a good hash function? Well, there are many elements that make a good hash function, but most importantly is that the hash function must be deterministic. So what I mean by that is that if you put in a value into the hash function, for example, a letter, and it returns the number, let's say 1, then if you run it again, it must return the same value. So the second attribute of a good hash function is if it is uniform. So what I mean by that is that every expected input is spaced out very evenly throughout the entire hash table. So for example, if every single space was filled like this, then this would be considered uniform. However, if we had a hash table like this, where maybe we have a lot of them scrunched up here, but then we have nothing that's filled down here, then this would not be considered uniform. So in other words, every expected input has an equal probability of being placed throughout. So the third attribute of a good hash function is continuity. And what continuity is that the expected inputs relative to how similar each input is should be how far apart they are in your hash table. So again, using numbers as example, so if our expected input was 0, 0, 1, 2, 3, 4, it should be ordered similarly as 0, 1, 2, 3, 4 in our table, and not something like 4 all the way there and then 0 all the way down here. So you want them to be relatively spaced apart in comparison to how similar they are in actuality. And last but not least, a good hash function should have as little collisions as possible. So what this means is that you want the hash function to generate as few conflicting values as possible. So if we run hash of A and we get the value of 1, and then we run hash of B and get the value of 1, then that's bad. And this is considered a collision because it returns the same value for 2 different inputs. So when we're actually trying to implement this into our array, let's say this is index 0 and this is index 1, then we place A into here, but then when we're trying to put B into the same exact slot, then we have a collision. And so this brings us to our next topic, and there are a few ways to avoid such collisions. So now, how do we avoid collisions? There are two main ways to avoid collisions. First of all, there's something called linear probing. So linear probing is the concept that if you hit a collision, then you will place the element into the next index. So if we hash A and we get 1, and then we hash B, and then we also get 1, then to avoid this collision, what we do is that if this is index 0, 1, 2, and we already have element A inside index 1, and we can't place B into the same index, then we'll just place B into index 2 in the next one. And then likewise, if we hash, let's say we hash C and it also gets a value of 1, then we'll go through here, we'll see that there's no space, B, there's no space, and then we'll put C into index 3. However, using this method, there are some problems. For one, there could be clustering problems. So if you have a lot of inputs that keep colliding, then eventually this chain will get longer and longer, and that's just bad for the hash table. So alternatively, a better way is, so the second way to avoid collisions is using something called chaining. And this involves using linked lists. So now bringing back this picture, we got our array again. Let's say 0, 1, 2, 3, 4 indexes. And then now instead of being an array of char or string, for example, now the array is an array of nodes that point to the head of a linked list. So every single element in this array is now a node. And so if we run hash and we get 1, for example, on A, and then we hash again and we get B, and we get 1. So with this, when we first place A into the hash table, the head will point towards our element A that we placed into index 1. And then now that we got a collision, we're going to go back in and place B right here. But now instead of pointing towards A, we modify it so that it points towards B. And then now B then points towards A. And like so, now we have a linked list. And we can keep doing this for as many elements as we want. And if we get another one that returns a different value, then all we have to do is point this head towards that value. And we got another linked list right here at index 4. However, ultimately, the best case scenario is if there's only one element attached to each head of the linked list, because ideally, then we would have the fastest runtime. Because if we had a single extremely long chain of elements, then the runtime would be nearing O of n linear time. However, having just one attached to each index would get us closer towards O of 1, and that's what we want. And that will be concluding my presentation on hash tables.